Okay, students, in today's session, we will be discussing regarding that particular model of conventional encryption technique. So as we have done in the case of a network security model, that how we can utilize all these basic components of this any type of a cipher model that if we are using. So I hope so that you are clear with that particular part. But now in this particular session, we will be discussing that if we need to follow the conventional encryption technique, that how basically an encryption technique is implemented in a system. So we will be discussing that particular model for the same. Okay, so we can start like this. Like as you know that whenever a topic is conventional encryption technique. That will be your conventional encryption technique. Okay. So the first thing is that we need to have a particular message here. So we are having that particular message source will be there, and then we need to follow a proper encryption algorithm. That is encryption algorithm, and then we have some decryption algorithm here. Then we will be defining some decryption algorithm to just recover that particular message. Okay, so this is the to just recover that particular message at the destination. So we are not discussing any numerical concept here, but we will start with this particular part. Like there is a source of a message here, and on this particular message part, we have to apply some particular encryption algorithm, and from that encryption algorithm, again we will apply the decryption algorithm at the destination. Okay, so at the destination end, we are following this particular technique. Now the next thing is that each and every algorithm will be using some key source over here. Each and every algorithm will be having some particular key source over here, and that key will be transferred to a proper secure channel. So that particular key will be transferred to a proper secure channel here to the decryption part. Okay, so this is the secure channel that we are having, that will be maintaining whatever the keys that we need to use in that particular process. Fine. So we are working like this. Like we will now. This is the main. We can say that a basic model that needs to be followed in case if we want to implement that encryption and the decryption part on the particular system. Fine. So now we will starting like this. There is a message source. Now let's suppose I represent this particular message source. Now let's suppose I am representing this particular message source with the value x. Okay. So I am using the value x over here. Then on this particular message source, like let's suppose this is the message I need to transfer. So this is the message source that I am using, and on this particular message I am applying some particular encryption algorithm here. Okay, so I am applying some particular encryption algorithm here for that particular part. What I mean now, let's suppose after encryption, whatever the cipher text that will be shown, that will be in the form of y. Okay, that will be in the form of y here. Now this y will be having, it will be equal to E, that is your encrypted message. Okay. Now how, on which particular part it is applying that particular encryption, that is E. First of all, we will represent the key over there, that is key K. So what key source we will be using, that is the K. Okay, so we are representing a plain text with value x, and we are representing our key with the value K. Okay, so when we need to apply this particular encryption algorithm on this particular plain text, what will happen? It will be implemented like this, that we will be receiving the value y, that will be my ciphertext, and we are applying that encryption on you with the help of this particular key, that is k, on the value x. Fine. So this is the main funda of your encryption algorithm. So what you are doing in the encryption part, that you need to use this particular plain text along with the value of k just to receive the value of the ciphertext. So this particular ciphertext will be having the value e, that is the encryption part that you are applying on this particular plain text with the help of a key k. Okay, so with the help of a value p, k, you are doing this particular. Fine. Next is the decryption part here. So you can see here like this. Okay. So again, when you will be applying that particular decryption part, you will be getting the value x here. You will be getting the value x over here like this. So this is how we can represent that particular message part. So at the destination, we will be able to get that plain text in the form of a x that we have represented over here. Okay. So this is how we can say that with the message x, with the message x and the encryption key k, with the message x and the encryption key k, the encryption algorithm forms the ciphertext. It will form the ciphertext 1. Okay. So with the message x and the encryption key k, it will form the ciphertext as y. Okay. So y will be representing your ciphertext here. Okay. So what we can y, that will be like y equal to y1, y2, so on till y. So we can write like this: y equal to e k comma x. Okay. So that is y equal to encryption of that particular plain text message with the help of a key k. Okay. So this is how we have generated that particular formula at the time of the encryption. Okay. So this particular notation y is produced by the encryption algorithm. Okay. So encryption e as a function of a plain text x. Okay. So we are using the value or the particular function that is x with the help of a key that is k. Finally, we are generating that particular ciphertext y, where we have applied encryption on this particular text x using the key value k. Fine. So this should be very much clear in your mind. Why so? Because further when we will be implementing all those algorithms at that particular part, you must need to recognize that what is the encryption part, what is the plain text you are using, which particular key you will be using for that particular plain text, and how your that answer, how that ciphertext will be received. And from that particular ciphertext at the destination point, how you can receive your plain text. So if we go towards the destination part, now what will happen? It will be working in the reverse manner. So how it will be working in the reverse manner? Here we will be representing, we want to get that particular x part. We need to receive this particular x part, which is my plain text. So here, what output you are getting? You are getting as x. Okay. Now this x will be equal to d. D will be your decryption part. Okay. You are implementing the decryption algorithm at the destination side or the receiver side, or we can say that any source that is any node that required to receive that particular actual text message. Okay, so we are representing x equal to b, and finally we are having that k again with the help of a k. Okay, so I just write it again. So we can get this particular message, that is x equal to, that is decryption k comma 1. Okay, so that is x equal to decryption of y. Y is what? That is a ciphertext we have received. What y is representing over here, that is a ciphertext. Now we are implementing that particular key on this particular ciphertext message. Okay, so we are representing this particular key on the ciphertext message in order to get the plain text message. Okay, so in order to get that plain text message here, we need to apply the key on the ciphertext. Okay, so this funda will be followed during the process of this encryption and the decryption part. Or we can say that when we need to follow the conventional encryption technique, at that time we require this particular portion. Okay, so this is how we can represent this particular structure for conventional encryption technique. Fine. Now, the next part that we will discuss here, we will elaborate this particular diagram in more detail. Okay, so we will be elaborating this particular formula with a more detailed manner. Like here again, I just make another diagram to find that the process will remain the same. But what we will be trying to show, that we will tell us that what type of keys that we are using. Okay, so it will represent us that what type of a keys that we will be using. So we can just define it like we are having that plain text input. We are defining like plain text input will be there again in the form of a x. Now here what we will represent, that we will be representing a secret key here. Secret key that is shared by, like if you remember in the last diagram, same key k was used by the sender also and was being used by the receiver also. Now in this particular diagram, we are just defining in just a more elaboration part that how we can use all these things. So we are representing secret key shared by sender and the receiver and the recipient. So we are defining this particular part with the value k. Okay. So here also in this particular part, we are representing encryption algorithm. So we are using some particular encryption algorithm, like we have AES is there, DES is there, that we will be discussing further in our these sessions. Okay, so we will be implementing all those encryption algorithm here, so that plain text will be having all those input that we can define. Okay, so any type of a input in the form of a plain text, we are representing that particular part here. So here we are using a secret key that is shared by sender and the recipient. Now here we will transmit the ciphertext. So obviously when we are encrypting particular message, what we are doing? We are just receiving the ciphertext message. So we are getting transmitted ciphertext. Okay, so this is your transmitted ciphertext here. Transmitted ciphertext here, where how do we have represented? Y equal to E, that is the encryption part. We are applying with the help of a key K to the message X. Okay, so Y equal to encryption K to the message X. Okay, next what we do, we will again use that decryption algorithm here. So we are having that decryption algorithm. So what is that decryption algorithm? That will work reverse of your encryption algorithm. Okay, so decryption algorithm will be working reverse of your encryption algorithm. So we are having this decryption algorithm here. So in this particular decryption part, what we will be doing? Again, we will have using that particular key, that is K. Now, where it will get the value of K? That is being shared by this sender bar. So your sender is sharing the same key with you. Your sender is sharing same key with you. That is a secret. So just remember, same key is being used by the sender part and the receiver. So we can write like this, like secret key. Again, we are representing secret key shared by sender and the recipient. So just remember one thing, that in the case of a conventional encryption technique, we were using only the same key over here, that is being shared by both the sender and the recipient part. So we are working like this, K and K for both the encryption algorithm and the decryption algorithm. And finally, what we are getting over here? So what value we are getting? That is after decryption. We are getting the value as what value we are getting? That is X. X is a plain text value we need to receive at this destination. So X equal to, now we will apply the decryption algorithm with the help of a key K on the value. On which particular part we are applying that particular decryption algorithm? That is 1. That is 1. Okay, so that is X is equal to B, K and Y. So that we can receive the plain text here. Okay, so this is how you can represent your conventional diagram in case of a keys you are using. So in the previous diagram, we were just mentioning that we were having key and we are passing that key from a particular secure channel. Why we require a particular secure channel in order to transmit the key? Because this key is a secret key. This key is a secret key. We have a unique key. So these are some features of this particular key. So what this key is having a particular feature? One is it is a secret key. It is a single key. And it is a shareable key. Okay, so just remember 3S for that. It is single key, or a same key we can represent. Same key that will be used for encryption part, and same key we are using for the decryption. Okay, single key, shared key, and the third one is it is a secret key. It should be kept secret only. Why so? Because we don't want any external entity to get this particular key, because it may help him to just decrypt that particular key. So we have to make this particular key as a secret key. Fine. So now this was all about the encryption algorithm. So just remember this particular diagram so that in future, if we need to implement the different algorithm, you must understand that how we can, what particular terminology or what particular structure that we need to follow in order to encrypt any particular message. Okay, so this is regarding that particular how this conventional encryption model works on. Now, the next thing that we need to discuss here is that now we will discuss a new topic. We now, as we have discussed the structure of this particular conventional encryption model, we have discussed that how encryption is possible, at which particular place we need to apply encryption, and at which particular place we need to define the decryption. Okay, by keeping that particular structure in your mind, now we will be discussing with particular encryption algorithm. So obviously, if we are having some particular encryption model, simultaneously that decryption model will also work for the same, but it will work in the reverse order. Okay, so every encryption model will be, we will be having that particular decryption model. That decryption model will be working same as that of the encryption part, but it will be working in the reverse. Now we will discuss all the encryption technique that we are again and again mentioning in a structure, that we need to use some particular encryption algorithm just to convert my plain text to the cipher text. Okay, so now we'll start with the classical encryption techniques. It is classical encryption. Classical encryption techniques are there. Okay, so that is classical encryption techniques are there. So we basically we have two basic building blocks. So we are representing two basic building blocks. Two basic building blocks in case if we need to mention the different encryption techniques. Okay, so we have two basic building blocks here. So one of the method is that we represent it as a substitution technique. Substitution techniques. So we are using a substitution techniques here. Another part is the transposition technique. Transposition techniques are there. Okay, so we are representing this classical encryption technique with two basic building blocks. One is your substitution techniques and the another one is your transposition technique. Okay, so the other technique is your transposition techniques. Now, how we can represent each of this technique? So we will discuss one by one. So first technique that we need to follow here is the substitution technique. So first technique that we need to discuss is the substitution technique. That is substitution techniques. Okay. So in this substitution, as the name specify, that we need to substitute the value of some particular character or a digit or a particular symbol. So what in this particular substitution technique is there, that it is the one in which the letters of the plain text are replaced by the letters or they are particularly replaced by a particular letter, a number or a symbol. So in substitution technique, just remember that letters of plain text are substituted or it is replaced by other letter, symbol or digits. Symbols or digits. Okay, so we can represent like this. We can represent this particular part that in the case of the substitution technique, so the letters of the plain text, PT is defining your plain text here. So letters of the plain text are being replaced by other letters, symbols or the digits here. Okay, so this is how we can represent this particular substitution technique. Fine, like we have in like let's suppose I am writing ACE2. Okay, so what I want that I should replace this A with X, C with Z, E with B, and T with N. So any type of a substitution I can give. Okay, so some particular word is there. So what I will do, I am just replacing that particular character with some another character. It can be a character, a symbol, or a digit could be. Fine. So this is how we can represent a word substitution. Now the next thing is that is a transposition. Another part is the transposition part. So another thing that we can represent, that is the transposition. Transposition techniques. Okay, so transposition is what? That we are somehow performing some sort of permutations on that particular word. Okay, so we are performing some permutation on that particular word. So we can say it like this, that permutations on the plain text. On the plain text. So what it will do, permutation means it is reordering. It is not adding any new character in that particular word. Okay, so it is not adding any new character in that particular word, but it is just reordering. Okay, reordering, you are just reordering here. You are rearranging. Okay, so rearrangement of the letter could be there. So that is how permutations are done. So rearrangement of the letters are there, or it can be reordering all those letters. Like in the previous example, we have discussed that we have represented A with X, C with any other character, E with another character, and T with another. But here, what will happen now? Let's suppose I am having this word ACT. So what I am doing, I am just rearranging all this. I am writing like this: C A T E T. Okay. Then I can write like this: E C A T T C E A, so on. Okay, so what we are doing, we are not adding any new character, or we are not replacing, doing any type of replacement in that particular lecture. What we are doing, we are just reordering the character in that a particular word. Okay, so we are just rearranging all those characters. So that is the part of this is transposition. Okay, so now we will discuss one by one all these techniques, that what basic method we use, how all these transposition techniques occur. So we will discuss all this part one by one. Okay. So we will start with the substitution techniques here. Okay. So we will start discussing the substitution technique. And substitution technique is a part of your, is a basic building block of your classical encryption technique. So we are representing as substitution techniques. Substitution techniques. So what the name specify? Substitution means that we are substituting any one character or a particular, we can say that digit by some another character, digit, or a symbol. So just remember the name, that how we can represent this substitution, that we are representing that particular, substituting that particular character with some another character. Okay, so there are different, we can say that types in this substitution technique, or there are different methods in your substitution technique, and I just write down all those methods that we will be discussing in this particular part. Okay, so like in substitution technique, we will be discussing following algorithm over here. So the very first part is your Caesar cipher, that is Caesar cipher. Okay. Second one is your mono alphabetic cipher. Mono alphabetic cipher. Then we have poly alphabetic cipher. We have poly alphabetic cipher. Then we have player cipher. We will be discussing the player cipher. Okay. Then we are having Hill cipher. Hill cipher. then we are having this cipher. Okay, and after that we will be discussing one time pad cipher. Okay. So these are some of the, we can say that, types of the substitution techniques that we will be discussing under this category of substitution. Starting with the Caesar cipher, then we have monoalphabetic cipher, polyalphabetic cipher is there, plain pair cipher is there, Hill cipher is there, and finally we have one-time pad cipher. So we will be discussing all these algorithm one by one. This is just falls under the category of substitution techniques. So if somebody asks you that give example of the substitution technique, we can just discuss all this, that we can just define all this also. Okay, so the very first part is the monoalphabetic substitution techniques. So we are defining monoalphabetic substitution technique. So that is monoalphabetic substitution technique. So in this monoalphabetic substitution technique, what will happen that a single cipher alphabet for each plain text, a single cipher alphabet for each plain text alphabet is used throughout the process. That means it is giving us fixed substitution. Fixed substitution. Fixed substitution is there, and how we can represent this fixed substitution? That a single letter, single cipher alphabet for each plain text is used throughout the process. Is used throughout the process. Throughout the process. That means if we have substituted any character, any plain text character with some another cipher text, that will remains the same. Now let's suppose this is my plain text, my name. Okay, so what I am doing here, like I am representing this M with N. Okay, so Y with P. Again, I am having this N. Okay, so that N will be, I am representing with O. Let's suppose I am representing this A with B. Again, I got this particular M. So how I have substituted that M with the value N? So I will follow the same thing over here. E, or finally we can have that. So what I need to say that if I have substituted any single character with a particular alphabet, that will remain same throughout the process. So let's suppose if I define that I am replacing this particular M with this particular N, so it will remain same any number of times when it will get the same character in that particular plain text. Okay, like I am writing like my name Meena. Okay, so again that M will be changed to N here, and I am getting this E over here. So again I have represented this particular E with Z. So I am writing like this Z. Again I am getting this N. So how I have represented this N with the value O. So there is O and A with B. So I am writing like this. Okay. So fixed substitution is there. So once if you use any type of a ciphertext for a particular plain text, it will remain throughout the process. It will remain same throughout the process. So it has a fixed substitution, a single cipher alphabet for each plain text. And the third thing that you can remember, that is whatever the relation between a character in the plain text to the ciphertext will be always 1-to-1. 1-to-1 relation between plain text and ciphertext. Okay, these are the three features of your monoalphabetic substitution. Fixed substitution, same character substitution will be there. Next is that one-to-one relation between the plain text and the ciphertext. Fine. So this is how we can represent a monoalphabetic substitution here. Next is the case that where we can represent a polyalphabetic substitution. So next we can have polyalphabetic substitution. Next is the next substitution category is, so this is the second category that we are discussing, polyalphabetic substitution. So in this particular word polyalpha, poly means many. Many times you have used this word poly, that means many. So here no fixed substitution is there. No fixed substitution will be there. That means we can change any character in the plain text with any number of a different that is ciphertext. Okay, so no fixed substitution is there. So there that means occurrence of a character may have different substitutes. May have different substitutes. Okay, so we can write like this: no fixed substitution is there, and occurrence of a particular character may have different substitution. So different substitute could be there, that we can have more than one substitute for a same letter. One substitute for same letter. More than one substitute for same letter. Okay, more than one substitute for the same letter. Now, okay, again I can write like this. I am writing like this: my name. So in the previous example, like let's suppose I am representing N. So I have used Y for this adding a new character here, that is P. Again for this N I can have O, and for A I was having B. For this M part, now it's not compulsion for me that I have to write N in place of M. That is required if we are using a monoalphabetic substitution. But in case of a polyalphabetic substitution, you can add any other character here like this, T. Again, I can have E. I can use any other value, that is F would be there. Again, for M, like here I am representing that M with T. Now I can represent this M with S. One to many. Here I was representing this M with N. Here I was representing with T, and here I am representing with S. Same case go for the E also. If I have represented this particular E with F, now I can write like this G. I can write like H. And for N again, we are having the same O, but I can change this value to P. And for A also, I can change this value to D. Okay, so no fixed substitution is there. You can use any other character for this. Okay, so what type of a relation we are having? So in previous case, we are having the relation between the plain text, in the relation of a character in the plain text to the ciphertext as one-to-one. But here you can have one-to-many. So we can represent like this, that one-to-many relation is there between the plain text and the ciphertext. Okay, so these are the three features of polyalphabetic. That the first, there is no fixed substitution. So occurrence of a particular character may have different substitute. Okay, so more than one substitute could be there for a single letter. More than one. Okay, so I can write like this: greater than one, more than one, substitution for the same letter. So again, I have shown that particular example, that is one to many relation is between the plain text and the set. Fine. So this is all about that we are having for this polyalphabetic substitution. Now the third type of the substitution that we will discuss here is a Caesar cycle. Is the Caesar cycle. So we can represent this particular Caesar cycle technique. Okay, so this is a third type of the substitution technique that we are having, that is a Caesar cycle. Now we are still in the process of substituting algorithms. So first algorithm that we have done in case of substitution, that was monoalphabetic. Second, we have discussed polyalphabetic, and the third one that we are going to start is the Caesar cycle. Okay, so what is the Caesar cycle? It is also called as shift cipher. It is also known as shift cipher, and it is also represented as additive cipher. Additive cipher. Okay. So what? So here, what will happen? That each letter in the plain text, each letter in plain text is replaced by a letter corresponding to number of shifts, corresponding to number of shifts here, number of shift that you are mentioning. So number of shifts in the alphabet, number of shifts in the alphabet. This thing you need to remember. So what we are doing in this particular Caesar cycle, that we, no doubt we are replacing some particular letter, but with a particular formula, as in the case of a polyalphabetic and monoalphabetic, what we are discussing, that we are randomly deciding any number, any character over. But here we have to follow a particular logic here, where we need to replace a letter in a plain text by a letter corresponding to number of shifts in the alphabet. Number of shifts in the alphabet. So this particular type of a Caesar cipher is a type of monoalphabet. Monoalphabet. Because we are fixing its substitution part. Monoalphabetic. Okay, so this is a type of monoalphabet. Fine. We are having a fixed number of shifts, and we are following the same formula for each and every character that belongs to that particular plain text. Clear? So this is a monoalphabetic Caesar cycle. On here, what will happen? Now let's suppose I am having this word A, B, X, C. Okay, so that is A, B, X, C. What key I am using here? It is key equal to 3. That means any particular character will start from this particular. Okay, that any particular, what number of shifts that we are representing, that is a 3. So what we'll be doing over here? Now let's suppose, as you know, that we are having a total 26 letters. Okay, so how we are representing that, if we are representing this particular part with a value of a E3. Now after A, if we move to the third letter, so what will we be having? That is B, C, D. So how we are changing its value? A to B. Fine. Again, if we are using that B, So if we follow 3 shifts over here, so how we can represent C, D, E? So this is okay. Similarly, we can have C. For C, we are having that F. Okay, and let's also on we are having different values. And if we move towards the X, so what value will X will be having here? So how this particular value of X will be represented? So X, Y, X, if we see after X, so Y, Z, A. Because after Z we don't have any alphabet. Okay, so it will move towards A. It will just follow the reverse pattern. So for X we are having A. For Y we will be having Z, A, B. So we are representing with it. Okay, and for Z we are having A, B, C. This is a 3-letter shift that we are using. Fine. So same type of a substitution will work on this particular part. Like we are having this A. So A will be represented with B. B will be represented with E. X will be represented with A. And C will be represented with. So this is the word that we are getting. Okay. So this is the, we can say that a ciphertext message that we will be getting here. That is the D, E, A. Fine. So this is how ciphertext works upon. So basically, Caesar ciphertext, how this particular Caesar cipher works. So basically, it was developed by Julius, that is Julius Caesar. Name of the inventor was Julius Caesar here. So that's why, due to his surname, we have defined this particular substitution as Caesar cipher. Okay. So it used an additive cipher to communicate with his officer. Basically, so it used all this method of shift to just communicate with its colleagues. So that's why he developed this particular method. So later on, it was being named on its surname only. That is a CC cipher. Okay. So like again, we can have some particular example. Now let's suppose I am using example a zebra would be zebra. Z-E-B-R. So how we will represent Z? That is with value C. How will we represent with E? That is H. How we will represent B? That is with E. And if you think about R, so how we will be representing, that is U. And for A, we are using the D. Okay, so this is a ciphertext that we can get to it. Fine. So we can also mathematically show this particular Caesar cipher with this. So I am just going to erase all this example. So there is another way that how we can represent this particular Caesar cipher in the mathematical way. So we are representing it as like this ciphertext. So how we get this ciphertext? C is your ciphertext. E, we have to perform that encryption with the help of a key on the plain text. That is, P is a plain text. So if you remember the starting of the lecture, we have done that structure part. So we have used this particular notation. So in case of this particular part, how we representing this particular part, that is P plus K mod 26. So here we will be using this particular concept for the Caesar. So basic model is this. For Caesar cipher we are using this P plus K mod 26. Okay. Next again for decryption part we are having, for decryption we need to receive the plain text. So we are using this decryption on with the help of K on the ciphertext. Again, we have discussed this particular portion in your this concept of the convention encryption. So this is how we can get that plain text decryption. K, comma C. K is a key. C is the ciphertext that we get. But in case of the Caesar cipher, how we can represent this particular part? That is C is the ciphertext minus K mod 26. Okay, so that is C minus K is mod 26. So if your this C minus K comes out to be negative, so if this particular value, if it comes out to the negative, then we have to add 26 to it. We will be adding 26 to, okay. So we will be adding that 26 to it if we get the negative. Add 26. Clear? So this is how we can represent this particular Caesar cipher. Okay, now let's take one example with us. So we can write like this. So what we do that from A to Z, we will represent it in the numeric value. We will be assigning numeric value here. Numeric value. We will be assigning a numeric value here. So we will start, total we are having 26 characters, but we will start from A as 0 and Z will be represented as 20. So A0, B1, C2, so on till Z equal to 25. Okay, so we are representing this value as starting from A to 0 to Z to 20. Now let's suppose we are having message hello. Now this is the example that we are going to start. That is message hello. Okay, so let's suppose my key is 4. This will require for the encryption part your plain text and your key part. So using that particular numeric notation for that, we will be ciphertexting each and every character in this particular plain text. So C of H, that is ciphertext of H. How many characters we are having? 1, 2, 3, 4, 5. So we will be applying the formula for this particular to each and every character in this particular plain text. So we are having C of H. So what was the formula? P plus K mod 26. P plus K mod 26. So what is the value of this plain text? So we will represent this H. If we follow this particular numeric pattern, the value of this H, that is plain text, is 7. What key is given? 4. And what answer? Mod 26. So after doing all that calculation, what value we will be getting? That is 11. So again, we will represent this numerical character with a value in the alphabet. So if we go to this particular series, what value for 11 we are having? That is L. So I again repeat, with the help of this example, we are having C, or we will take the next character here, E. Using this particular formula, what is the value of E? Like we have A, B, C, B will be 3, E will be 4. Okay, so E will be 4. So we are representing 4 plus, what is the value of E? That is mod 26. So after doing all this calculation, what value we will be getting? 8. So 8 is being represented in this particular numeric chart as we are representing as arms. Okay. Next, again we are having hello. We are going for this L part. So this L part will be having the value. Plain for this, the value of this L part is 11. Again 4 mod 26. So what value we will be getting here is that after doing calculation we will have it 15. Okay, so 15 is being represented with the character P. Again we are having L, so we don't perform the same calculation. By default it will be P. By default it will be P. And last is the O, C, O. Okay, so the value of O is 14 in this particular chart plus 4 mod 26. So what answer we are getting here? 18. So 18 is represented with the word S. So what is my encrypted message here? L I P P S. Yes, this is my ciphertext. Okay, so this is L I P P S. So this is representing my ciphertext. Fine. So if we go to the decryption part, what will happen? Now we will perform that decryption of that particular algorithm using that notation that we have mentioned earlier. So what decryption part that we are getting? So if you remember the formula, now this is the cipher part. We will be using this particular cipher part to receive the plain text after applying the proper decryption algorithm. So what was the decryption algorithm? That now we are representing P. We need to get the plain text. So again we will do character by character here. P of L. So what was the formula? That is, what was the formula that we are having here? That is C minus K. C minus K mod 26. This was my formula. Now, what was the ciphertext value for this particular character? What is the ciphertext value of this particular character? That is P of L. P of L. We are using this particular part. P of L is there. So that is L minus 4. K will remain the same. P will remain the same. Mod 26. So what is the value of A? That is L11 minus 4 mod 26. So what answer will we get? That is the 7 value we will get. That is H. Clear? Again, we will work on I. This is the ciphertext we are having I, and we are having I minus 4 mod 26. That means we again get the value of I from this particular chart. So what was the value of I? That is A minus 4 mod 26. 8 minus 4 mod 26. What value we will be getting here? 4. And this 4 is represented with the word, with the character P. Okay. Then we have P. P is there. So we are representing it as P is representing with the word with the this numeric value 15 minus 4 mod 26. So that is what answer we are getting here. That is 11, and the value will be 5. So again we are having for this P part, the same answer we will be getting. Now last is the P of S. So again what we will be doing? C ciphertext. What is the value of this S? Here from this particular chart, what value of S we are having? 18 minus 4 mod 26. And what answer we will be getting? 14. 14 is represented with the word O. What it has generated? HELLO. This is how we are received that particular plain text. HELLO. This is the O. So you can do it manually also, plus you can do it with some particular formula also. Okay? So we have given that particular formula. If you want to calculate in the part of the numerical part, so you can use the same. Fine. So this was all about Caesar cipher part. You just remember in the case of the Caesar cipher that it is also represented with the word shape cipher, and the additive cipher is there. What we are doing here, we have to assign some particular numerical value to each and every character. Otherwise, if you are having any key value, like we are using key value here 4. So if you want to use any particular key value, so manually also you can change the value with that particular shift that is being that you have to do according to the key value that is given. Otherwise, there are two formulas for encryption also and for decryption also. You can follow that particular formula in order to get that particular character at the respective time. Okay, so this was all about Caesar cipher, and I think we are done with this today's session. So thank you very much for patiently listening.